Now, here's something that's really neat, and I hope you appreciate it as much as you should when you finally master it. It's not the easiest thing we've done in the course. It's one of the harder things we've done, probably not the hardest. And it takes a little sorting out and quite a bit of practice to really understand the process, but this is a pretty typical mathematical process. And once you know it, you have some significant mathematical knowledge. Let's start with some data, some y versus x data. Let's let x be 1, 2, 3, and 4. And let's let y be 4, 16, 36, and 64. Now we can notice these are every other perfect square, and we could probably figure out what the function is that gives y as a function of x. And we'll easily be able to validate the function when we do find it. But we're going to find that function by a process that I call linearization. And we're going to linearize the function as follows, okay? Since we see that these are perfect squares, maybe it would occur to us to linearize using the square root function to undo the perfect square. Okay, so let's take the square root of all the y's. We'll write our x's down as they are, but we'll take the square root of every y. Now the square root of 4 is 2, the square root of 16 is 4, square root of 36 is 6, square root of 64 is 8, and we know that. So that's pretty obvious. And now it becomes pretty obvious that we have the same rise between every 2 points, and the run is the same between every 2 points, which means we're going to have the same slope between every 2 points, which means that this graph now has a straight line, or this table now has a straight line or linear graph. This is how we say we've linearized the table. This table wasn't linear. The rise kept getting bigger, rise of 12, rise of 20, rise of 28, while the x increment stayed the same. So if we graph this, it's not going to be linear. Now the point is, if it's not linear, we can't fit a straight line to it, and it's pretty easy to fit a straight line. So we've linearized the data, and we're going to be able to fit a straight line if we graph that data. X equals 1, 2, 3, 4, y equals 2, 4, 6, 8. I haven't drawn a y scale here. The function that fits this data is y equals 2x. Now we could actually see that easily from the table. Now if we double x, we always get y. But if our data is a little bit messy, we won't be able to see that sort of thing. And we're going to have to make a table and do a best fit straight line, find the equation of the line, and go from there. But in any case, in this case, we do get a function we can be confident of. We get y equals 2x. And that's the fit that works for the linearized data. And it's a perfect fit. Now that we've fit our linearized data with a y equals 2x function, we're going to unlinearize it so we can get back to our original function. What did we do to linearize this data? We took our data and we transformed it by taking the square root of all our y values, right? Well, let's come over here and square all our y values. If y equals 2x, then when we square all of our y values, we're going to have y equals the square of 2x, or 4x squared. Okay? So y equals 4x squared is what we get when we unlinearize the y equals 2x function using the inverse of the function that we linearized it with. Okay, the square root of y function linearized it. What's inverse to that function? Y squared. If we apply y squared, squaring all our y's, which are equal to 2x, we're going to get 4x squared. Okay? Now let's go back here and see if y equals 4x squared fits this data. Well, you should pause and see that it does. Okay? Now if you paused or not, whether or not you paused, if we square x, we get 4, and multiply it by 4, we get the right value. If we do 4x squared on 2, x squared is going to be 4, we multiply that by 4, well, we get 16. How about that? Now square 3, we get 9 times 4 is 36. Square 4 times 9, 4 times 4. 4 squared is 16 times 9 is 64. So lo and behold, it works. So let's step back and look at the entire process. The process is we start with some data, we linearize it, we get a good linearization, in this case a perfect one, we get a linear fit. Then we use the function that's inverse to the one that we used to linearize to unlinearize, and we get a function that in this case is a perfect fit to the original data. So we've discovered the function that works for the original data. Now that's kind of neat. And I'll also note that from this point on, once you've mastered this, the course starts to get easier. It doesn't get real easy, but it gets considerably easier. This is the peak of the hill for this course, and it's all downhill from here.